My name is Harper Mangine, and this is Physics 2211 Lab 3, Spaceships and Black Holes with the Universal Force of Gravitation. So, introduction and purpose. So, the purpose of part 1 was to analyze the gravitational motion behavior of a star to compute the mass of a black hole. And the purpose of part 2 was to model the motion of a moon around a planet to practice coding for gravitational forces, velocities, and position update. We also had a little spaceship that we had to calculate initial velocities for. So the results of part 1, my FNet, perpendicular, parallel, and normal were all very large numbers, times 10 to the 27th and the 28th. And then the mass of my black hole was essentially 1.5 times 10 to the 34th. The second results, my ship speed in the x direction was negative 22,800. And then my ship speed in the y, I chose to do it in relation to the moon speed, just because any value that I had been putting for the y direction was not lifting off. So our important principles, Newton's second law, F net equals delta P over delta T, where delta P is mass times the change in velocity. And this is basically saying that the acceleration of the body is directly proportional to the net force acting on the body and inversely proportional to the mass. And then these labs were really big on the universal force of gravitation, which is F equals G mass 1, mass 2 over R squared, which R is the distance between the two masses. And then in the second part of the lab, I also had to use the velocity update formula and the position update formula with the spaceship. So for the black hole code, the seed was my GT email. We had to calculate the initial and final locations and velocities, and then find our delta V and our delta P, and then also calculate delta P over delta T, or I guess technically the derivative dP dt, and we set the net force equal to that. We also had to calculate the unit vector of position, and also had to do the net force in the parallel, perpendicular, and the change in the perpendicular. And then the mass of my black hole was just, I did it, you can have the option to do it in more than one line. I did it in one line. So from left to right, this is kind of what the code looked like running. The perpendicular and net force were greatest when the star was in line with the black hole closest. The R was the shortest. And then also the parallel force was never really that huge. So this is the second code. This is the spaceship code. I had to calculate all of the forces, the net force on the moon, which was split into gravity on the moon by the planet, on the moon by the spaceship, and then the net force of the spaceship, which was the force of gravity on the spaceship by the planet, and then the force of gravity on the spaceship by the moon. And then also the last section on the right over here is just applying Newton's second law, updating position and updating velocity. So this is my spaceship model. The first one, it was just, this had orbited twice. The second one, the orbit started shifting to the left because it kept coming in close contact with the moon. So the moon's gravitational pull changed the trajectory of the spaceship. And then the last one was my attempt at trying to get it to do a figure 8, but that is incredibly difficult, just because it's a simulation, and also the motion of the moon and the motion of the spaceship are not necessarily the same. And also, since they're both moving at the same time, they would have to line up perfectly every single time for the spaceship to make a figure 8, but around both, using both the planet's gravitation and the moon's gravitation. And then those are all my forces on the side, all very large numbers. Possible sources of error: simulation does not directly model reality. The initial velocities were trial and error. And we're also assuming that they exist in a total vacuum with no other celestial bodies, even though we know in space there's lots of stuff floating around. Lab questions. So for the first one, the net force and the change in momentum, we set them equal to each other. And the net force, if we were to do it on paper, would be incredibly difficult to calculate since you'd have to calculate all of the forces acting on the systems. And then, but the change in momentum is pretty easy because it's just the change in time and velocity. And then if we were to add the black hole, the star, the planet, and the moon and the spaceship all together, you'd have to add the gravitation of the black hole and the star. And so the black hole is the most massive, so it would have the most gravity, and everything would end up orbiting the black hole instead of orbiting one another. Thank you.